Picture this. You're falling, faster than you ever thought possible, past the ultimate point of no return. The universe outside vanishes, the screen goes black, and instead of getting stretched into subatomic spaghetti, you suddenly pop out in a totally different galaxy. Sounds like something ripped straight from a late-night sci-fi marathon, right? But hold on a second. Just last month, two independent teams, one at the legendary Caltech, the other all the way over at the University of Tokyo, were running fresh, cutting-edge gravitational wave models. And what did they find? Weird, persistent echoes that absolutely refuse to fit the profile of any normal, garden-variety black hole we thought we knew. Their preprint, a paper that's already setting the physics world on fire, dropped onto rciv.org just 3 weeks ago, and it's already racked up a mind-boggling 47 citations. Suddenly, that old joke, black holes are where God divided by zero, feels less like a punchline and more like a boarding pass to the greatest adventure imaginable. So, are we actually staring down the barrel of the universe's most lethal, yet incredibly efficient subway tunnel? Or is this just another mind-bending, math-induced mirage, a trick of the cosmic light? Stick around, because the answer to that question flips, twists, and turns more times than a gymnast before this video ends, and I promise you, the final flip is still making the world's top experts sweat. This isn't just theory anymore, it's getting real. Okay, let's put the sheer scale of this into perspective. If you somehow manage to fire a bullet from Earth at the speed of light, the absolute fastest anything can travel, it would still take you an insane 100,000 years just to cross our own home galaxy, the Milky Way. Think about that for a second. An entire 100 millennia. But a wormhole? A black hole shortcut that actually works? That could theoretically do it in, well, probably less time than it takes you to eat your lunch. And today, for the first time in history, the cold, hard numbers are finally starting to lean towards maybe. Seriously, maybe. For the longest time, when physicists talked about a black hole's event horizon, they'd often quote the classic line from the Eagles song, "You can check out anytime you like, but you can never leave." That's because, according to general relativity, the event horizon really is like the ultimate one-way cosmic Hotel California. Once you cross that boundary, there's no going back, ever. And it's not just because the gravity is incredibly strong, though it absolutely is. The real kicker, the truly mind-bending part, is the geometry of space-time itself. Inside the event horizon, space isn't just curved, it's flowing inward. Think of it like being on a waterfall that's moving faster than you can swim upstream. No matter how hard you try to paddle out, the current of space itself is pulling you relentlessly towards the singularity, that infinitely dense point at the center. Every single direction you could possibly move in, every future for you, points directly to that crushing, inescapable singularity. For nearly 60 years, that felt like the absolute, definitive final word on black holes. Even Stephen Hawking's Nobel-worthy work on black hole evaporation, which showed that black holes aren't entirely black and can slowly radiate away, still essentially assumed that any information falling in was ultimately lost forever inside. It was a cosmic cul-de-sac, end of story. Then came 2019. The Event Horizon Telescope collaboration delivered the first direct image of a black hole's shadow, specifically the supermassive one at the center of the galaxy M87. And it was glorious. It showed the predicted photon ring, a bright halo of light circling the black hole, exactly as Einstein's theory had foretold. It was a triumph of science and engineering. But then, if you looked really closely, there was something else. A faint, almost imperceptible secondary ring, or perhaps a subtle distortion within the primary one that nobody had explicitly asked for. The Event Horizon team, being cautious scientists, initially shrugged it off, attributing it to limited resolution, or perhaps just noise in the data. But you know who didn't shrug it off? The theorists. They immediately ran the numbers, plugging in various exotic possibilities, and what they found sent shockwaves through the community. That tiny, unexpected extra ring, that subtle distortion, perfectly matched the theoretical signature of a wormhole throat. A traversable wormhole throat. And just like that, the headline avalanche began. Well, way back in 1935, two pretty smart guys, Albert Einstein and Nathan Rosen, were playing around with the equations of general relativity. They noticed something fascinating. If you mathematically glued two Schwarzschild black hole solutions back to back, what you got wasn't just two separate regions of space-time, but a theoretical tunnel connecting them. They called it an Einstein-Rosen bridge, what we colloquially know as a wormhole. This was a purely mathematical construct, a theoretical shortcut through space-time. The trouble is, the original Einstein-Rosen bridge was, well, a bit of a cosmic joke. It pinched off faster than light could possibly traverse it. Imagine trying to run through a tunnel that's collapsing in on itself at supersonic speeds. You'd be squashed flat before you even made it a meter inside. So, it was less like a cosmic metro system and more like a cosmic mousetrap, utterly useless for any kind of travel. For decades, wormholes remained a fascinating but ultimately impractical mathematical curiosity. Then, fast forward to 1988. A brilliant physicist named Kip Thorne, along with his colleagues, decided to revisit the problem. They calculated that if you could somehow thread the throat of a wormhole with negative energy, a truly bizarre type of matter that weighs less than nothing, and that actually has negative mass or energy density, then, and only then, could the wormhole stay open long enough for something or someone to pass through. This was a game changer, but it came with a colossal catch. No one, not ever, has actually bottled negative energy. It sounds like pure fantasy, right? The closest we've ever come to observing anything remotely like it is the incredibly subtle Casimir effect, where two uncharged metal plates squeezed incredibly close together in a vacuum show a tiny, measurable energy deficit. It's a quantum phenomenon, and the amount of negative energy involved is absolutely minuscule. The problem? Scaling that up to a size that could keep a stellar-sized wormhole open would require more negative energy than the positive energy contained in the entire Milky Way galaxy. Yeah, that sounds like a pretty definitive deal-breaker. Except, here's where it gets even weirder. Quantum field theory, the bedrock of modern particle physics, doesn't actually put a hard cap on how negative energy can go. It only demands that the total energy, when averaged over time and space, must remain positive. Think of it like a cosmic credit card. You can borrow quadrillions and go wildly into debt, as long as you pay it back fast enough. So, while it still feels like pure science fiction, the math doesn't entirely rule it out. And then last year, something truly remarkable happened. Gravitational wave chirp GW21-091, its ring-down phase, the final vibrations of the newly merged black hole, carried incredibly faint echo frequencies. And these echoes were spaced out exactly like what you'd expect from a traversable wormhole throat. The paper is still under intense peer review, so nobody's popping champagne just yet. But that signal? It's sitting there, winking at us, daring us to look closer. So what sparked this renewed interest and the possibility of these echoes? It wasn't just one big eureka moment, but rather the convergence of two truly groundbreaking theoretical breakthroughs. First, we have the brilliant work of physicists Juan Maldacena and Xiaoliang Qi. They constructed what's called a toy model, a simplified theoretical universe, where two black holes could actually share a common interior, connected by an emergent wormhole. The crucial part? This model preserved something called unitarity, which is a fancy physics term for saying that information is never truly lost. This was a massive deal, because it offered a potential solution to the infamous black hole information paradox, a problem that's plagued physicists for decades. If information isn't destroyed, then maybe there's a way out, or a way through. The second breakthrough came from a group of researchers at Ruden University. They took the standard Friedmann cosmology, which describes the expansion of our universe, and plugged in a very specific, yet theoretically plausible type of matter, dust-like matter. These aren't the kind of dust bunnies you find under your bed. These are pressureless particles, behaving in a way that's reminiscent of matter in the very early universe.
What they found was astonishing. By introducing this dust-like matter, they could construct traversable wormhole solutions that didn't violate any known energy conditions, which are fundamental rules about how much energy a region of space can contain. Put these two breakthroughs together, and the equations start telling a wild story. If the cosmos feeds a black hole the right kind of diet, meaning if there's enough of this exotic, pressureless matter around it, then the event horizon, that dreaded point of no return, could potentially morph into a stable, traversable throat. Think of it this way. The same way the internal pressure of air keeps a balloon perfectly round and open, this exotic matter pressure could theoretically keep a cosmic tunnel from collapsing. We still haven't directly observed this specific type of exotic matter, but here's the kicker. The cosmic microwave background, that faint afterglow of the Big Bang, hints strongly at the existence of extra-relativistic species, basically unknown particles or fields that were zipping around in the early universe. Some theorists are now tagging these as the very missing ingredient needed to stabilize these wormholes. And let's not forget the biggest mystery of all. About 95% of our entire universe is made of dark stuff, dark matter and dark energy, that we can't directly detect or even fully understand. In that context, exotic starts sounding less like cheating in physics and more like simple accounting for the things we just haven't found yet. The universe is full of surprises, and it might be holding a very big one for us. All right, let's talk about these echoes that are causing such a stir. When two black holes, those cosmic behemoths, finally collide and merge into one, the newly formed larger black hole doesn't just sit there silently. Oh no. It vibrates, literally ringing like a gigantic cosmic bell. And when it rings, it emits gravitational waves, ripples in space-time itself, that have a very specific, pure tone. This tone then fades away exponentially, like a bell's sound slowly dying out. It's a beautiful, elegant process predicted by general relativity. Now here's the crucial part. A wormhole merger, or at least a black hole that might be connected to a wormhole, would produce something very similar. But with one tiny, yet utterly profound difference. A faint, secondary after echo. Imagine that cosmic bell ringing, then a moment of silence, and then a second, softer, almost ghostly ring. And the really important detail? The frequencies of this after echo would be integer multiples of the primary ring. This specific spacing, this particular rhythmic pattern, is a unique fingerprint, a telltale sign of a reflective throat, something that would bounce gravitational waves back rather than just absorbing them. The LIGO and Virgo gravitational wave observatories have been incredibly successful, logging an astounding 93 confident detections of black hole mergers so far. And out of those 93, a tantalizing 7 have shown evidence of these 3.8 sigma echoes. Now, 3.8 sigma isn't quite the gold standard 5 sigma statistical certainty that physicists usually demand for a definitive discovery. That's where the sweating experts come in. But here's the thing. The odds of random noise producing that exact pattern, those specific echo frequencies, are roughly 1 in 4,000. That's not impossible, but it's certainly enough to make you sit up and pay attention. We're on the cusp of a new era in gravitational wave astronomy. Next-generation detectors like LISA, which will be orbiting in space, and the Einstein telescope, a colossal underground observatory here on Earth, promise to drop the noise floor 100-fold. That means they'll be exponentially more sensitive. So, if these echoes are real, if they're truly the universe whispering about hidden tunnels, we'll know within the next decade. Until then, the safest bet is still silence, the conventional black hole. But the wildest bet? That's a brand new cosmic subway map just waiting to be drawn. Okay, before we all start packing our bags for Andromeda, let's pump the brakes just a little bit. As the old adage goes, extraordinary claims require extraordinary evidence. And while 3.8 sigma is exciting,
It just ain't that. Not yet, anyway. There are plenty of smart critics out there, and they're quick to point out that these echoes, intriguing as they are, could potentially be produced by a whole host of other exotic but perhaps less mind-bending cosmic phenomena. We're talking about things like the super-dense crusts of neutron stars, or hypothetical boson stars, which are made of a different kind of particle entirely, or even hairy black holes, a theoretical variant of black holes that have additional properties beyond just mass, charge, and spin. Any of these could, in principle, create similar gravitational wave reflections. And here's another very plausible alternative. Imagine a black hole merger, but something falls back into the newly formed black hole. Say, a rogue clump of matter from the accretion disk that was swirling around it. That falling matter could reflect some of the gravitational waves, creating a fake echo that looks suspiciously like a wormhole signature. The only way we'll really be able to tell the difference, to definitively distinguish between a true wormhole and these clever imposters, is by stacking dozens, perhaps even hundreds of these events. We need to analyze whether the echo strength and frequency scale exactly, precisely in the way that wormhole math predicts, rather than how other objects would behave. Current sample size for these echoes? A grand total of 7. We need a lot more data, and we need it soon. But even if, against all odds, a traversable throat does exist, there's another absolutely brutal hurdle that popular articles tend to gloss over: tidal forces. You know how the moon creates tides on Earth? Imagine that, but cranked up to a literally universe-shattering degree. These forces would stretch a human being into what can only be described as cosmic linguini, long before you even reached the other side. The math is merciless here. Spaghettification happens in microseconds for objects falling into typical stellar mass black holes. You'd be a string of atoms before you could even scream. The only black holes that might give you a survivable ride, where the tidal forces are gentle enough at the event horizon to keep you from instantly becoming a noodle, are the supermassive ones. Those colossal beasts millions or even billions of times the mass of our sun. But ironically, those are precisely the objects whose echoes are the hardest to detect, because their gravitational wave signals have incredibly low frequencies, making them difficult for current detectors to pick up. So yes, a gateway might exist, but stepping through it could very well feel less like a glorious journey and more like a very, very aggressive trip through a wood chipper. So with all these theoretical possibilities and observational tantalizers, how close are we to actually putting this to the test? Right now, one of the sharpest, most promising tests involves polarized light. Think of light waves as oscillating in different directions. When light passes through certain materials, its polarization can be rotated. A wormhole's throat, if it exists, is predicted to act like a birefringent crystal. It would rotate the polarization of light in a very specific, predictable spiral pattern. This is a unique signature. The Event Horizon Telescope, the same one that gave us the M87 image, is planning its next major run in 2025. And this time, they'll be gathering 230 gigahertz data, which should allow them to resolve light polarization down to an incredible 0.1% accuracy. That's precise enough to tell the difference between a conventional M87 black hole and a wormhole, if that difference is truly there. It's like getting a cosmic fingerprint. Meanwhile, another incredible instrument, the Gravity Plus instrument on the Very Large Telescope in Chile, is meticulously tracking the orbits of stars incredibly close to Sagittarius A star, the supermassive black hole at the very center of our own Milky Way. If there were a wormhole lurking there, even a tiny one, it would induce a slight, subtle wobble in the Newtonian orbits of those stars, a wobble that a pure, conventional black hole simply wouldn't cause. It's a different kind of gravitational signature, a gentle tug that could betray a hidden tunnel. And it's not just telescopes and observatories. On the theory side, quantum simulation labs are pushing the boundaries of what's possible. They're building intricate cold atom circuits, essentially tiny quantum computers, that are designed to obey the exact same equations as curved spacetime. It's like creating a miniature controllable universe in a lab. And get this, just last April, a Google AI group, using a 1D chain of 40 superconducting qubits, managed to create a system whose ground state geometry mimicked a traversable wormhole. The most astonishing part? When they teleported a qubit, a unit of quantum information, the dynamics of that teleportation perfectly matched the predictions of the Sachdev-Yekitaev model, which is a theoretical framework predicted by none other than Maldacena himself. Now let's be super clear. This isn't a real wormhole you can jump into. It's a quantum simulation, a model. But it's the very first lab system where information effectively vanished in one spot and reappeared in another without physically passing through the intervening space. These are baby steps, absolutely, but this baby isn't just crawling anymore. It's starting to walk, and it's walking in a very, very interesting direction. All right, let's zoom out for a moment and consider the truly mind-boggling implications of all this. What's the ultimate so what if wormholes are real?
If these cosmic shortcuts actually exist and can be traversed, then interstellar travel, the stuff of dreams and science fiction, flips from being impossible to merely engineering hell hard. You'd still need to survive the most extreme journey imaginable, but once you reach the supermassive core of a black hole, you could, in principle, exit somewhere else, perhaps even in the Andromeda galaxy, without having to cover that mind-numbing 2.5 million light-year gap in conventional space. Think about that for a second. That would fundamentally rewrite everything: economics, warfare, and even the very survival of our species. The universe would suddenly become a much smaller and infinitely more accessible place. More likely in the near term, even if we can't hop through them ourselves, wormholes offer a clean, elegant solution to the black hole information paradox. Remember that problem we talked about earlier, where information seemed to be destroyed? If wormholes preserve unitarity, it means the universe makes sense again, that nothing truly vanishes into oblivion. Preserving unitarity is the kind of quiet, foundational breakthrough that lets physicists sleep soundly at night, even if tourists can't yet buy round-trip tickets to other galaxies. It's a profound shift in our understanding of how the universe fundamentally works. And what if they're not real? What if all these echoes and theoretical models are just fascinating dead ends? Even then, the echo data isn't useless. It's still teaching us incredibly valuable things about other exotic, compact objects, strange cosmic entities we never even knew existed. It's pushing the boundaries of quantum gravity, one of the biggest unsolved mysteries in physics, into testable territory. We're finally getting empirical data that can confirm or refute some of the wildest ideas about the very fabric of space-time. Either way you slice it, the next decade of observations, with our new generation of telescopes and detectors, is poised to completely flip our cosmic script. We're on the verge of discoveries that could redefine our place in the universe. So, after all this, are black holes actually secret gateways to other galaxies? Today, the honest, most accurate answer is still probably not. But here's the kicker, and it's a massive one. The gap between probably not and definitely not just shrank from a colossal canyon to a tiny, tantalizing crack. The math allows it. Fresh gravitational echoes are flirting with the possibility, and upcoming, incredibly powerful telescopes and experiments are gearing up to probe it with unprecedented precision. Whether the universe actually cashes that amazing theoretical check depends entirely on matter we haven't yet seen, living under conditions we can't yet create in a lab. One thing, however, is absolutely certain. The final word on this isn't going to come from armchair speculation or late-night debates. It will come from more data, from better detectors, and from the relentless, insatiable curiosity that keeps humanity staring into the dark, mysterious depths of the cosmos. So, keep watching the skies, because the next echo we hear, that next ripple in space-time, might just be the universe whispering, "Roads? Where we're going, we don't need roads."
If you want to be among the very first to know when those groundbreaking 2025 polarization images drop from the Event Horizon Telescope, or when the next gravitational wave echo sends shockwaves through the scientific community, then you absolutely need to smack that subscribe button right now. And don't forget to ring the notification bell so YouTube's algorithm doesn't bury these crucial updates.